So, I'm reading the question all over again. What does the statement that the specific heat capacity of aluminium is 913 joule per kilogram per Kelvin mean? What does this statement mean? That the specific heat capacity of aluminium, capacity of aluminium is 913 joule per kilogram per Kelvin mean? Meaning, what does this statement mean? Then a block of metal initially at 100 degrees Celsius is gently immersed in a large copper calorimeter of mass 80 gram, containing 500 gram of water at 28 degrees Celsius. If the final temperature of the mixture is 40 degrees Celsius, calculate the heat capacity of the block. Take the specific heat capacity of water to be 4,200 joule per kilogram per Kelvin. And then the specific heat capacity of copper to be 385 joule per kilogram per Kelvin. So I'm giving you 5 minutes, okay, 6 will do, to go through this question, after which we'll all look at it and then continue whatever we have for the day. So start with 6 minutes. Please, the question is on the platform. And let me hint this. This is one of, I think, WASSCE question on calorimetry. I'm here to check the year though. So go through it for 6, 7 minutes. Then we'll all discuss it. Let me check attendance. So I have Elizabeth here. Julian, Cadmiel, Crispin, Leslie, Millicent, Priscilla, and Sappho. The rest are still resting. Okay. Those of you who are here, thanks for being here on time. So you are calculating for the specific heat capacity of the metal, or of the metal block. Elizabeth, Frida,
Yes,
Julia,
please.
what and what are gaining the heat energy? Okay, Mami, yeah.
The calorimeter and the water.
Good. So heat loss by the block, okay, must be equal to Q gain or gained by calorimeter and water. Okay, so clearly this must be the expression. So we have Q by calorimeter plus Q by water. How do we express the heat loss by the metal block in this case? How do we write the heat loss by the metal block in this case? Anybody, any idea? Any idea from one of you? We want an expression for the heat loss by the block. How do we write it? Or, yes, what is the relation for Q loss by the block? Yes. Elizabeth, any idea? Julian?
Please, I think it will be C times change in temperature.
Which of the C? Because we
The
have
specific the heat capacity.
Why do you think so? Elizabeth, why do you think it must be heat capacity?
Please, I know that the math was not given first of all, and I know that C is equal to Q over change in T. And so making Q the subject, yes.
Thank you. You see, so mass of the block is not given, then the specific heat capacity of the block is also not given. So you can't express the energy loss in terms of the mass and specific heat capacity. Moreover, the question also asks that we find the heat capacity of the block. So we have C times change in temperature to be the value of the heat loss by the block. Therefore, this C times delta T must be equal to the mass of the calorimeter is given, specific heat capacity of the calorimeter is given, times change in temperature, plus mass of water, specific heat capacity of water, times the change in temperature. So this is the expression which will help us find a specific heat capacity, the heat capacity of the metal block. So class, make me proud. Finish it for me. Complete it for me. So Elizabeth is here. I'm checking attendance. Frida, Julian, Cadmiel, Calvin, Crispin, Kweku, Leslie, Mamia, Michelle, and Nana Safo. Attendance today is so bad. Well, maybe they will join. My handwriting today is not as I personally want it, so you just bear with me. I'm just gradually mastering the use of the smart board. So pardon me for my handwriting, which I don't personally like. So after going through it, in fact, we'll also solve it. I'll solve it with you so that you can use that to assess the work you have done as well. Are we through? Class, are we through? Okay, so let's do it. And you use that to assess what you've done. So C What will be the change in temperature for the metal block? What can somebody help me with the change in temperature for the metal block? Hello, what is the change in temperature here for Keolos? Mamiya. Mamiya.
Yes, please.
What's the change in temperature for the energy loss by the block?
100 minus 40.
So 100 minus 40. This is equal to the mass, but the mass of the calorimeter is 80. Let's change 80 to kilogram. So we have 0.08, right? Times the specific heat capacity of the copper is given to us as, what's the value of the specific heat capacity of copper?
385.
So this is 385. Okay. Then the change in temperature. What's the change in temperature? What's the change in temperature here?
40 minus 28.
40 minus 28. So this will also be 40 minus the initial temperature, which is 28 degrees Celsius. So this will be 8 for the heat gained by the calorimeter. Then let's calculate for the heat gained by the, okay, once we are putting everything together, let's add. The mass of water is 500. So 0.5 times specific heat capacity of water 4200 times the same change in temperature 40 minus 28, which is 12. Okay, 12. Therefore, C times, what is 100 minus 46?
54.
So this is 54.
This is 100 minus 40.
40.
Pardon?
It's
100 minus 40.
And temperature at equilibrium. Okay. I think I've written that as 46. Thank you. This is 40. Okay, so that is 60. That is 60. Thanks for the correction. This is the reason why you must also be following the discussion. Okay, so put the heat gained by the calorimeter together for me. 0.08 times 385 times 12. Put them together for me.
369.6.
Okay, so this is 369.6. Okay, plus then put together the heat gained by the water for me.
25,200.
Okay, so 25,200 200. Okay, therefore, help me determine the value of C. Help me determine the value of C.
Please, I had 426.16.
426.
Okay, so this is 426.16. And what's the unit of heat capacity? What's the unit? What's the unit of heat capacity?
Joule per kilogram per Kelvin.
No.
Kilojoule.
Don't forget C.
Oh, joule per Kelvin.
Yeah, joule per Kelvin.
Joule per Kelvin or joule per degree Celsius. Okay. So because changing temperature on the Celsius and then Kelvin scale is the same. This is it. So this is a typical WASI question.
On your year, are you in gas? Are you in gas?
Okay, this is a typical WASI question. Leslie.
Mr. Edia, please, I don't understand why we subtracted the temperature of the mixture from the initial temperature of the block. Because for what I did, I just found the heat capacity of the
Hold on.
calorie.
Leslie, hold on. Let me mute all and then you come in, right? Please, those of you with your mics on, mute yourself for me. Leslie, then come in.
Mr. Edia, please, I was asking that why are we subtracting the temperature of the mixture from the initial temperature of the block? Because for what I did, I just...
Okay, Leslie, your question is clear. The initial temperature of the block is will certainly be greater than the temperature at thermal equilibrium. You see, temperature of the mixture is temperature at thermal equilibrium. Okay, so the idea is that the block with a higher temperature will lose heat energy to the calorimeter and then to the water. And so if you are looking for the change in temperature, because the initial temperature of the block will certainly be greater than the temperature of the mixture, we subtract the initial higher temperature. Okay, we subtract the temperature at thermal equilibrium from the initial higher temperature of the block. The reason why the change in temperature becomes 100 minus 40. Leslie, are you clear with this?
Yes, please.
Then,
thank you.
Then for the other part, you see the water and then the calorimeter will be gaining. So their final temperature at equilibrium will certainly be greater than their initial temperature. The reason why we are subtracting the initial temperature, which is 28, from the final temperature, which is 40, because the cal and water will gain. So their final temperature will certainly be greater than their initial temperature. I hope you're okay.
Yes, please.
All right. Julian. Julian, are you there? Julian. Hey, Julian is not responding. Elizabeth, what does the statement that the specific heat capacity of aluminium S 913 joule per kilogram per Kelvin means? What does it mean? By the statement that the specific heat capacity of aluminum is 913. Yes.
It means that 913 joules of heat energy is needed to be liberated by a unit mass to change its temperature by 1 Kelvin.
Hey, Elizabeth, you are correct, but I won't give you 4 marks. Okay, let me hear from Kelvin as well. Kelvin, please talk to me. I know you are here. Kelvin, talk to me. Okay, let me leave it open. Whoever is ready to share what you also think with me, please, you are free to express your view. All right. Is that Leslie? Okay, Leslie, go ahead.
Mr. Edia, please, I think it means that 913 joules of heat energy is required to raise the temperature of a unit mass of aluminum by 1 Kelvin.
So be specific. It's required to raise the temperature of 1 kilogram mass of aluminum by 1 K. So 1 kilogram mass of aluminum must absorb or liberate, okay, 913 joules of heat energy in order to change a temperature by 1 Kelvin or 1 degree Celsius. All right. So that's the meaning of the statement. 1 kilogram mass of aluminum must be absorbed or liberated in order to change the temperature of 1 kilogram mass. So, sorry, aluminum, 1 kilogram mass of aluminum must absorb or liberate 913 joules of heat energy in order to change a temperature by 1 Kelvin or 1 degree Celsius. That's the meaning of the statement. These are simple questions to actually score everything in class. Okay, I'm going to send another question. We are actually trying. So when you get it, do not be disturbed. Yes, let's see what you can do. So give me some time to forward. Good. This one, I will not interact. You solve it because there are answers. I want to see how you would solve to get the result. So it's been sent to the group. A piece of copper of mass 2 kilogram at 100 degrees Celsius is quickly transferred to a block of ice at 0 degrees Celsius without heat loss. Determine the mass of ice that will melt. The specific heat capacity of copper is 400 joule per kilogram per Kelvin. The latent heat of fusion of ice is 3.3 times 10 to the power 5. So a piece of copper of mass 2 kilogram at 100 degrees Celsius is quickly transferred to a block of ice at 0 degrees Celsius without heat loss. Determine the mass of ice that will melt, given the specific heat capacity of copper to be 400. Then the latent heat of fusion of ice is 3.3 times 10 to the power 5 joule per kilogram. So latent heat of fusion must be joule per kilogram. Per Kelvin is wrong. So start work. The answers are there, A, B, C, and D. Let's see what you can be able to produce from this question. Start work. 5 minutes. While I take note of attendance. Is somebody true? Leonard. Leonard. Michelle, are you true?
Sir, please. I think the answer is B.
Is D.
B.
B as in boy.
Yes, please.
Okay, we shall see. Crispin is also getting B. Okay, Michelle, go ahead. Or you have called out your answer.
Yes.
Okay. All right, let's go through the question. Let's go through the question. So, I'm retrieving the main question. All right, so a piece of copper of mass 2 kilograms at 100 degrees Celsius is quickly transferred to a block of, so mass of copper, we have 2 kilograms. So M of copper is equal to 2 kg, and its initial temperature T is 100 degrees Celsius. It's quickly transferred to a block of ice at 0 degrees Celsius without heat loss. Determine the mass of ice that will melt, considering that the specific capacity of copper is this, and then latent heat of fish. Okay, so you see, because the initial temperature of the ice is 0 degrees Celsius, when you give it any amount of heat, it would melt, because the temperature given is at the melting point of ice. So any extra heat energy that is given to it, it must melt. Okay, so the copper will lose heat energy to the ice. So heat loss by copper okay, by copper must be equal to heat gained by ice, gained by ice. Now, heat lost by copper can be determined by its mass, specific heat capacity, times the change in temperature. And this heat lost by copper is what will cause the ice to melt. The ice is melting because its initial temperature is at the melting point of ice. So here, this will be equal to MLV. MLV, where M is the mass of ice that will melt. All right. So heat lost by copper 2 by, what's the specific heat capacity of copper? It's 400. So 400 times, what will be the change in temperature? Class, what will be the change in temperature? Hello, anybody? How do
I
we?
think
It will be what?
I think it will be 100.
So 100. 100 minus 0. This must be equal to M times specific latent heat of, please, this will be fusion. It's ice will melt, so fusion. Okay, and this is 3.3 times 10 to the power 5. Therefore, M would be equal to mass of liquid, which will melt, will be equal to 8 times 10 to the power 4 divided by 3 times 10 to the power 5. So what's the answer? What's the answer? What is the final answer? Mamiya, what is your final answer? Oh, class. No one is talking.
0.2424. That's what I'm getting.
24. This is times 10 to the power negative 1. Therefore, the mass M would be equal to 0.2424 kilogram. Do we have the answer in the among the options given? Yes, that is B. So those of you who called B, yes, you are right. How many of you got it right? Please raise up your hand if you got this correct. Elizabeth got it. Let me go to. All right, Leslie also got it. Then Michelle. More hands. Oh. And then Frida. Okay. All right. So that's it. Application of the knowledge in solving problems. I'm giving you a last question to try. Julian, are you there? Or Julian is gone?
Yes, sir. So I'm here.
Why you've not been talking? I've been calling you.
Sir, please, I'm on a quick errand.
Okay. Forward a last question to to you to try. Getting it is, I should have forwarded these questions. Okay. I'll forward the questions to you. This was the trial questions to you after the class. Okay, so question science. This is also another heat question under calorimetry. WASI. So the B question lists 3 main features of the clinical thermometer. Okay, that will be done in thermometry. Then explain why water becomes cooler when kept in a clay pot for some time in a room. This is a practical question which you can require the answer later from me. Explain why water becomes cooler when kept in a clay pot for some time in a room. Then, water of mass 0.4 loses 210 kilojoule of energy when taken from Earth's surface, the Earth's surface to mass of surface temperature negative 60 degrees Celsius. Water of mass 0.4 loses 210 kilojoule of energy when taken from the Earth's surface to mass of surface temperature negative 60 degrees Celsius. The water temperature decreases until the water freezes. The water temperature decreases until the water freezes. The temperature of ice formed decreases until it becomes equal to that on Mars. The temperature of ice formed decreases further until it becomes equal to that on Mars. Calculate the temperature of the water while on Earth. Calculate the temperature of the water while on Earth. And you are given specific latent heat of fusion of ice to be 3.3 times 10 to the power 5. Specific heat capacity of water for 4,200. And then specific heat capacity of ice 2,100. So you are to determine the temperature of the water whilst on Earth. Start work. Please collaborate. That you can discuss. Okay, you can discuss as usual. After everything, I'll go through it with you. So you share ideas. Let's see what you can do. After which, I'll discuss with you. I think 6-7 minutes will do. Start work. Leonard, I hope you can hear me now. Leonard. God, make me proud. You are not discussing. Oh. I've given you the chance to share ideas, but the platform is silent. Angel, Angel. Oh, Angel did not show up today. Eva Leslie is here. Okay, Angel noted. I think let's look at it. So the mass of water is 0.4 kilogram, and we are told that it loses 210 kilojoule of heat energy when taken from the Earth's surface to mass of surface temperature negative 60 degrees Celsius. The water temperature decreases until the water freezes, okay? And so the temperature of ice formed further decreases until it becomes equal to that on Mars. Calculate the initial temperature of the water. So let's go through the process. The processes involved is that water of unknown. So let the initial temperature of water on Earth be T. Let that be T. Okay. Now the question indicates that when it's taken to Earth, it loses a certain amount of energy, heat energy, and that is given to us as 210 kilojoules. Okay. Now the processes involved in losing that energy is that its temperature drops so the temperature drops from T till it freezes. So if we are to quantify the amount of heat loss or energy loss, it is mass of water times specific heat capacity of water times the change in temperature, and the change in temperature is T minus 0. It loses heat energy till it freezes. So the drop in energy from T, the unknown, to 0 is what we have indicated. Then after dropping heat temperature to 0, because 0 is the freezing point, water will begin to freeze. Okay, so the quantity of energy used in doing this would be M times LV, LF. Then after every water is frozen on Mars, don't forget we saw that change of state occurs at constant temperature. So when it reaches 0, the water will begin to freeze, and by the time every water changes to ice, the temperature will still be 0. Then the question further states that the temperature of the frozen water further drops till its temperature is equal to the temperature on Mars. So there is change in temperature here again. So M mass, of ice times the specific heat capacity of ice times the change in temperature, and the change in temperature will be equal to 0 minus 6. It further drops till its temperature is equal to the temperature on Mars, and the temperature on Mars is -6. And this is equal to the total heat energy lost by water, 210 kilojoules. Please, is there any question here? Is there any question here before we continue? Okay. So if no question, let's continue. Let's then put in numbers. What is the mass of water? The mass of water is 0.4. So 0.4 times specific heat capacity of water 4,200 times T. T is the temperature on Earth, which we don't know. This plus the mass of ice. Okay, the same mass of ice, mass of water is what will be converted to ice. So 0.4 again times specific latent heat of fusion of ice, which is 3.3 times 10 to the power 5 plus, okay, when every water has changed state to ice and its temperature is further dropping, okay, we have the same mass of ice. So 0.4 again is equal to specific heat capacity of ice, which is 2,100 times the change in temperature, which is equal to 6. This is equal to 210 times 10 to the power 3 joules. So this will be the equation we are going to deal with. So the rest is calculator work. The rest is calculator work. 4,200 times 0.4.
Lydia, please, it's 60,
But
not 6. It is 60, not 6. The MC in bracket.
the temperature on Mars.
Yes, please, it's negative 60.
Thank you. Thanks for the correction. So this is good. So we have this as 1680. 1680 T plus 3.3 this times 0.4, we have 132, 100, and we have this as 132,000. Then plus 0.4 times 2100 times 60.
50,400.
50,400. This we equate it to 210,000. Okay, so the next work to do is just to determine T, which is the temperature of the water on Earth. And this will be equal to 210,000 minus, let's sum this up. Let's sum 132,000 plus 50,400. This is
182,400.
182,400. And subtract it for me.
97,600.
Then let's divide through by 1,680.
16.4286.
So this is 16.42 degrees Celsius. So this is the temperature of the water whilst on Earth. And that is it. Please, any question here? So it's, you see, whenever the question is given to you, it's really not so difficult. But your understanding of the concept is really the issue as to how you can put the ideas together and then solve a problem. Solve the problem is the issue. Okay. All right. So I'll send or forward the rest of I'll forward the rest of the WASI questions and nakalometry to you so that you give it a try at your convenient time. Class, is that okay? So I want us to start with thermal expansion in solids. Thermal expansion in solids. Thermal expansion in solids. Do we know that when we heat solid, liquid, and gases, solids expand less, meaning that liquids and then gases expand easily or more than how solids expand. So solids expand less compared to please let me take this call and then get back to you. Okay, I beg you. All right, so solids expand less compared to liquids, how liquids and then gases do. So compared to liquids and gases. Yes, can somebody tell me the reason behind this? Why is it that liquids and gases expand more than solids do? Can any one of you share the reason behind this with us? Julian, Maria. Maria.
Compared to liquids and gases, we all know that liquids and gases have lesser intermolecular distance. The distance between the molecules are more free in liquids and gases as compared to solids. The solids molecules are tightly packed. So for it to expand, it will not be able to expand easily because the molecules that are coming to help it expand are packed.
There are no space.
There's no space. Yes, please.
Okay, so that's true. So you can explain this using the space between molecules of the three states. You can also explain this using intermolecular or interatomic forces. Molecular or interatomic forces between molecules. For solids, because the atomic or molecular forces between neighboring molecules or atoms is so strong, this is similar to if you have a spring connecting between two items or two people. If the spring is so stiff and then it vibrates, it will hardly shake. But if the spring is so loose and it vibrates, it can greatly shake and expand. And so because for solids, the intermolecular forces are too strong, when the molecules vibrate, they cannot easily be displaced. The molecules being displaced is what causes the expansion. But because this force is so stiff, it is hard for the molecules to vibrate. Is that okay? So it is because of the strong interatomic or intermolecular forces between solids, the reason for which it expands less. Meanwhile, for liquids and gases, because the force is so loose, when they vibrate, they can easily stretch out and then cause expansion. Is that okay? So that explains the reason why solids expand less compared to how liquids and gases do. Expansion in itself is caused by the average the vibration of the molecules. Okay, I'm not writing, or please, once I'm recording, please be attentive and then get the notes as well. Expansion in itself is caused by vibration of particles or molecules, and when they vibrate, okay, because they stretch out a little bit, the average distances between atoms or molecules increases. But this average distance between molecules is, when vibrated, is less in solids and more in liquids and gases. At a very small temperature, gases can expand so wide. Liquid can also expand, not so much as gases, but solids would expand less. Okay. Now solids undergo three forms of expansion. Solids undergo linear expansion, area expansion, and volume expansion. Whereas liquids and gases, because they have no shape, they can only go through volume expansion. So solids can go through three forms of expansion, whereas liquids and gases and gases only undergo volume expansion. And this is the reason for this is that, you see, liquids and gases have no shape. They only have volume. Whereas for solids, they have definite shape and then definite size, and then they have volume as well. So they can go through linear expansion, area expansion, and volume expansion. Okay. Now let's look at some applications of expansion in solid. Before we look at linear, area, and volume expansion, applications of expansion in solids. When we talk of applications, we are talking about uses. How is it used in everyday life or in any natural phenomenon? One typical application, okay, of application of expansion in solids is the, oh shit, please, I'm coming. Some applications of expansion in solids, we have linear expansion in bimetallic strip. Linear expansion in bimetallic strip. Please, today, pardon me, I'm coming. Hello. Omega, please forgive me. Today, the calls seems to be so much for me, unexpectedly. Okay, so forgive me. So linear expansion in bimetallic strip. What is a bimetallic strip? You see, bimetallic strip is a pair of joint metals of different linear expansivity, meaning the two metals joined or combined expands differently. Okay, and this is used in the thermostat of electric iron and then fridges. Okay, so bimetallic strips are used in electric irons and fridges, electric irons, fridges, ovens as a regulator of heat. If you have watched carefully, the thermostat of electric iron is such that, okay, when you control it, all right, when you control it, it connects by itself, and then when the temperature or the heat energy is so much, it also disconnects by itself. So automatically, the thermostat will regulate itself. Okay, this technology is used in fridges as well. So when you on a fridge, when at a certain temperature, it will cut by itself. It also works in oven. Okay, this is one classical application of expansion in here metals of different ability to expand. Another application of expansion in solids is the gaps in rail lines. Gaps in rail lines. You see, whenever engineers build a rail line, even concrete structure, it is not built in such a way that two ends fuse or join exactly. They need to leave gap. Leaving gap between caters for expansion in a solid. So when you build rail lines and you don't leave expansion joints, okay, as time goes by, the metals would expand and then meet. When they expand and then meet each other, it exerts great force on one another, and as a result, damages the structure of the metal. So to cater for expansion, you need to leave joints. Okay, so that is also one clear application of expansion, linear expansion in metals. You see, sometimes when you are in your room on sealed room, and then during hot afternoons, you hear some sounds on the roof or from the roof as if it is raining. That situation or feeling is due to the expansion, thermal expansion in the solid. Okay, so it's an application of the fact that metals generally go through linear expansion. Then another application of expansion in solids is expansion of pendulum wire in the grandfather clock. Expansion of pendulum wire of the grandfather clock. The grandfather clock is the old kind of wall clock which works on the principle of simple harmonic motion, simple pendulum. They oscillate. Now, such clock is the pendulum string is made of wire. And so with time, nothing is permanent, nothing is 100% efficient. With time, it is seen that because the wire is made of metal, it goes through thermal expansion. So it expands, and then as it expands, actually, it affects the accuracy of the timing because the period of oscillation of the wire is directly proportional to the length. So when the length is made of wire and it is expanding, it means that with time, the length will change. As the length changes, it affects the period of oscillation. Okay, so these are few of the applications of expansion, thermal expansion in solids. Thermal expansion in solids. All right, we have a lot, but I'm giving you 3, okay, so that you can get more example or more applications in books as well. Is there any question? Is there any question? If there's no question, let's look at linear expansion in solids. Linear expansion in solids. Solids can go through 3 kind of expansion. Expansion in length, expansion in area, and then expansion in volume. So we are going to look at these expansions one at a time. So linear expansion in solids. If you have a solid of length L, we have linear expansion in solids. So we have a wire of length L. We have a wire of length. So the original length of this is equal to L naught. L naught. So L naught is equal to the original or initial length. Now to cause an expansion in the length of wire L naught, what do you think are some of the factors which would affect expansion in this? Or what external factors would cause an extension or expansion in the wire of length L? In other words, what must we do in order to bring about expansion in this wire? Mami, any idea? We have a wire of initial length L. If we want to cause it to expand, what are some of the things we are to do to it in order to bring about expansion in its length? Kweku?
Apply high temperature.
So, okay, Kweku, go ahead with yours.
So I was going to say you heat it.
Okay, so what Mamiya and Kweku are saying is that the expansion, its linear expansion, E is directly proportional to the amount of heat energy or the change in temperature, delta T. The extent of expansion, apart from applying temperature, what other factors would affect the extent of extension within the wire? Apart from change in temperature, what other factors would affect expansion in the wire L0? All right. So the size, the initial length of the wire also affects the extent of expansion. Now, what it means is that we are looking at linear expansion. So if you have a wire of small length L, you equally get a corresponding expansion. If you have an initial longer wire, you get an expansion which will commensurate the length of the wire. So it is more like you get what you have. If you have small, you get small. If you have lengthy or longer something, you equally get a longer something. Okay, so the extent of expansion is also directly proportional to the initial length L0. Can we think of any other physical factors? So physically, we've talked about change in temperature. We've also talked about the initial length. Okay, so I think these are the obvious physical factors which will affect the expansion, meaning that the expansion E is directly proportional to L0 times the change in temperature T. Okay, E therefore is equal to a constant of proportionality times L0 times delta T. And this constant of proportionality K is what is represented as the symbol alpha, termed as coefficient of linear expansion. So the constant of proportionality K is known as coefficient of linear expansion, or sometimes instead of expansion, we also use linear expansivity. So either coefficient of linear expansion or coefficient of linear expansivity. From the equation, let's make alpha the subject, the coefficient of linear expansion the subject. Kweku, help me make the coefficient of linear expansion the subject from the equation developed. Kweku, or Kweku is gone.
K equals E over L and times change in temperature.
Okay, so we have E alpha is equal to E over L0 times change in temperature. Okay. Now, how then do we define coefficient of linear expansion or expansivity? The coefficient of linear expansivity is defined as the change in length per unit length per degree or Kelvin rise in temperature. Change in length per unit length per degree or Kelvin change in temperature. Change in length per unit length per degree or Kelvin change or rise in temperature. Meaning that delta T can be in degree or in Kelvin. So if upon subjecting external change in temperature to the metal, it will expand by this margin. Then what will be the initial or the final length? The final length after it's going through expansion, the final length L2, let's indicate that to be L2. L2 would be equal to the original length L0 plus the extension or the expansion E. Okay, so the final length after it has gone through linear expansion L2 will be equal to the original length plus that little expansion. Okay, and so L2 would be equal to L0 plus, if from this equation, if we make E the subject, we have alpha times L0 times delta T. L2 therefore would be equal to L0 out 1 plus alpha times delta T. The new length therefore would be equal to the original length L0, okay, times 1 plus alpha delta T, okay, in brackets. This will be the final length L2 when the metal goes through a small change in length. What do you think is the SI unit of linear expansivity alpha? From our equation, what do you think is the SI unit of, will be the SI unit of alpha? Can somebody help? We want to derive the SI unit of alpha. Michelle, what will be the SI unit of alpha? Hey, Is Michelle gone? Angel, you are here. Elizabeth, Eva, Frida. Okay, Elizabeth, from the equation, what do you think will be the SI unit of? Okay, Frida is ready. Frida, go ahead. Frida, go ahead. Hey. If Frida cannot hear us, let somebody else. Mamiya, what do you think will be the SI unit of linear expansivity? Mamiya,
Yes, please.
what's the SI unit?
I don't know.
Okay, Elizabeth is ready.
Please, I think that alpha will be k exponent -1. Oh,
K exponent negative where k is equal to,
like Kelvin.
yes. Mamiya, E is expansion. Expansion is actually E is equal to L2 minus the initial length L1 or L0, whichever way you want to call it. Okay, so E is change in length. E is actually change in at the final length and then the initial length. So what do you think will be the SI unit of the change in length? It's meter. So meter divided by the original length L0 has a unit in meter. Change in temperature can either be Kelvin or degree Celsius. So when you cancel out, the SI unit will be per Kelvin or per degree Celsius. Okay, that is why we are defining linear expansivity E as change in length per unit length per degree or Kelvin rise, per Kelvin rise or change in temperature. All right. Metals have different linear expansivity. The linear expansivity of aluminium, for instance, is equal to 0.000012 per Kelvin or per degree Celsius. Meaning that if you subject 1 meter length of aluminium to a temperature of 1 K or 1 degree Celsius, it will expand by this margin. Very, very, very small. Very, very, very small. Please, are we okay?
Yes.
Okay, so that is it with linear expansion in metal. So metal would go through this if it's just a straight length something. Now, if it's an area, if it's a sheet, if the metal is a sheet, something like this, then because this is the original length, this is the original width or breadth, B0. When you subject it to a change in temperature, delta T, please, delta T here is always the final temperature minus the initial temperature. So it can be initially when the length L0, the length of the metal is L0, its initial temperature is room temperature 24 degrees Celsius. Then after subjecting this, heating this, maybe to a temperature of 100, you want to calculate the extent of expansion. So the expansion, which is equal to the coefficient of linear expansivity of the metal times the original length times delta T. So delta T in this case will be equal to 100 minus the initial temperature of 24. Okay, so delta T is the final minus the initial. So if it's a metal sheet with initial length this and then initial width as this, after subjecting it to a change in temperature, the length would expand, the breadth would equally expand, and so this will go through area expansion. Okay, area or superficial expansion. Okay, so we will look at area expansion, and then if it's something with volume, if the metal is a voluminous something or has length, breadth, and height, then we'll look at how the volume expansion also would come in our meeting next week. Please, is there any question? Is there any question? If there's no question, then this is where we draw the curtains on today's meeting. We'll continue next week. May the good Lord be with you, take care of you, and guide you. Please take care of yourself. Review whatever I've given you. I'll post an assignment today so that you can, go through it and submit it as at when you finish. Until then, bye-bye.
Bye.
All right.